Hi and welcome to a lesson of multivariable calculus. So in this class, we are going to talk about a very important topic of multivariable calculus, that is the Stokes theorem. So Stokes theorem is one of the most beautiful and very important result in mathematics. In the previous lesson, we talked about the Green's theorem that was for regions in two dimension. For example, if we have a region R that is bounded by a curve, so this is the curve. For instance, this outside here is the curve, and we give it some orientation, say counterclockwise orientation. Let's consider that something is moving on this boundary in this direction, and uh, this region R is bounded by this curve C. This is the curve C, and let us consider that there is some vector field trapped inside this region, represented by F, and we can write it as P dx plus Q dy. So we can define the vector field this way. So now there might be some circulation inside this region, and we know that we can find that circulation using the Green's theorem, which says that the net circulation in this region R is equals to the line integral of this field over the curve C. So this is simply equals to the double integral of this curl over the region R dot kdA, where this k represents the normal vector, vector normal to this region, this normal vector n. So since this region is an xy plane, it's two-dimensional, so the vector that is normal is simply the vector that is parallel to the z-axis. Okay, so that's why we are taking this as k, since if it is parallel to the z-axis, then we don't have x and y coordinates, so we just have k here, right? So this was Green's theorem. Now Stokes theorem is a higher dimensional uh, case of this Green's theorem, which also says that if we have a surface instead of a region, now if we have a surface S and we can say that if, say, there is some vector field over this surface, or if there is some circulation over this surface S with boundary. So the boundary of this surface is this curve here. You can see that this is the boundary of this surface. This is the boundary with some orientation. This is the orientation of this boundary. So, and the surface itself has some orientation, and the orientation is simply given by the normal vector. And why we take it as a normal vector is that it simply uniquely represents the orientation, because if we have taken something else, some other vector that is not normal, then we might have infinite many vectors of that kind. For example, if I took a vector here, or suppose let's take a point here and consider that this is the tangent plane at this point. This plane is tangent at this point. Then if I took this vector that makes angle theta with this tangent plane, then I can have another vector here in this direction that makes theta same angle theta with the plane, and or in this direction or in this direction, that makes the same angle theta. So we may have infinite many vectors that makes the same angle theta with the tangent plane. But what the normal vector does is that it uniquely defines this orientation of the surface. Since if we have a vector that is normal to the surface, that is 90 degrees, making 90 degrees, so with the tangent plane at the point, so it is 90 degrees everywhere. And since we have this only this unique vector having this 90-degree angle, right? So that's why we take its orientation in the direction of normal. And the other way to think about this is that, for instance, if I take a smaller vector area element over the surface, say a piece here, a piece here, this piece here, and now if I want to find the area of this uh, little plane, now it looks like a plane, it's a very small element. It looks like a plane. So I need two vectors to find the area, because we know that the cross product of the vectors gives the area to the parallelogram. So if we have two vectors on this plane and we take the cross product to find the area, we get uh, another vector, but having a direction that is normal to both of these vectors. So that will be a normal vector to the surface here on the surface. So this is the concept behind giving the orientation to the surfaces. So Stokes' theorem, now more formally, it says that suppose S is an oriented piecewise smooth surface with a unit normal vector and bounded by the simple closed piecewise smooth boundary. So it's a boundary here. This is the boundary. This is the boundary C, and boundary curve, or we can say it Dawa S. It's a representation of the boundary. That is, Dawa S says that it's the boundary of the surface. Let this be a vector field whose components have continuous first partial derivatives in some open region containing S. Then we have this relation holds, which says that the line integral over the boundary, the line integral of this vector field over the boundary is equals to the surface integral of the curl, surface integral of the curl and ds, right? So this is what states the Stokes theorem, and it's a very important result in specifically in physical and engineering sciences, right? Now we will not embark with the proof of this theorem at this stage, but we will just take some problems and we will see how we can verify this Stokes theorem. Now consider this surface S here, represented by this equation z equals 4 minus x square minus y square, and we have discussed this in the section of quadratic surfaces, that this is a paraboloid, and one more thing here, we should write that z is greater than or equals to 0, which means that its boundary is sitting on the xy plane. The boundary curve, that is Dou S, or simply C, it is sitting on the xy plane. This equation here, this inequality suggests that its boundary is sitting on the xy plane. So z is greater than or equals to 0. It means that uh, it cannot uh, go beyond the xy plane. That is, it cannot go inside the xy plane. And now again we can see that the boundary curve is simply where z is 0, so 0 equals 4 minus x squared minus y squared implies that x squared plus y squared equals to 4. So the boundary of this surface is simply this circle of radius 2. Right? Now we can just verify Stokes' theorem for this particular problem. So let us uh, see what the problem says. It says that verify Stokes' theorem for the vector field F. So there is some field on the surface, defined on the surface, taking sigma to be the portion of the paraboloid. So sigma is the portion of the paraboloid, this paraboloid, and for which z greater than or equal to 0 with upward orientation. So the orientation is upward, means the vectors are pointing outward from the surface, and C to be the positively oriented circle. So the positively oriented means the counterclockwise direction. All right. And we will verify this, that is the left and right hand side of the Stokes theorem. So let's first consider the left hand side that says the line integral over the boundary curve. So f dotted with dr. Dr is nothing but it is simply a vector having these components dx, dy, dz, and f dot dr simply means 2z, 3x, 5y dotted with dx, dy, and dz. So it gives 2z dx plus 3x dy plus 5y dz. So the integral over the boundary will be this expression here. So now the boundary is, we already talked about it, that it is sitting on xy plane. So these terms having z simply vanishes. So these term vanishes, and we only left with the term with x and y. So we need to integrate this term only here, 3x dy. Now since this is a curve, and we can solve it simply by parameterizing this curve. So let's say x equals r cosine t and y equals r sine t, and r is 2. So x is 2 cosine t and y is 2 sine t. So for dy in terms of dt, we need to differentiate. So we get 2 cosine t. So dy is 2 cosine t and dt. So this integral becomes line integral over 3 times x, that is 2 cosine t times 2 cosine t dt. Now where t, the parameter t runs from 0 to 2 pi, since if we want to complete this circle using the vector, using this parameter t, we need to move it from 0 to 2 pi to complete one rotation. So it runs from 0 to 2 pi, right? So we can now simply integrate this one. So we get 3 times 2 is 6, times 2 is 12, 12 cosine square t dt from 0 to 2 pi, and solving this we will get 12 pi, right? Now we need to keep the record of this result, that is the line integral f, line integral of the f, force f. And now let us start solving the left-hand side. Left-hand side, that says that we need to find the surface integral of the curve. Surface integral of the curve. Now to find the curve, we need to find the determinant. We need to find the determinant. Partial x, partial y, partial z, and force is 2z, 3x, 5y. So we need to find this determinant for finding the curve. We will get 5, 2, and 3. Now we take the inner products. So for taking the inner product of curl with this NDS, we need this n. So n is a normal vector. We first need to find the normal vector. So find the normal vector. Now consider that this surface, is some level set of this function, and if we find the gradient of this function here, that is the function of x, y, and z, so we will get the normal vector to the surface, because we know that the gradient is normal to the surface. So if we differentiate this function with respect to x, we get 2x. Then differentiating with respect to y, we get 2y, and then differentiating with respect to z, we get 1. So n is 2x, 2y, and 1. Now we can take the inner product, 5, 2, 3, dotted with 2x, 2y, and 1 ds. So we get 10x plus 4y plus 3 ds over the surface S. And ds is nothing but it is simply dx dy. And since we are working on a surface, so we need to parameterize this to solve it very nicely. So let us parameterize the surface. Now for parameterization, it is important to see that what actually are the level curves of this uh, paraboloid. So the level curves of this paraboloid looks like these circles, right? So since we can see that the level curves are nothing but the circles of radius less than or equal to 2. So here we have the radius as r equals 2. Here we may have the radius r equals 1, and so on. And here we have the radius r equals 0. So r is running from 0 to 2. R is running from 0 to 2, and theta will be from 0 to 2 pi, because it's a circle, and for one complete rotation we need to go from 0 to 2 pi. So theta will be from 0 to 2 pi, and r will be from 0 to 2. And for the parameterization using r and theta, we just simply need x equals r cos theta and y equals r sine theta. Okay, so now this integral becomes 0 to 2 for r and 0 to 2 pi for theta, and inside we have 10x, so 10 r cosine theta plus 4r sine theta plus 3, and now simply this ds will be converted to r dr d theta, r dr d theta. Now we need to solve this integral to find the value of this uh, the surface integral. So we will get the result 12 pi after solving it. You can just verify the result. So earlier when we solve the left hand side here, you can see that we get the result 12 pi. So we see that the left hand side of this Stokes theorem equals the right hand side of the Stokes theorem equals 12 pi. So here the Stokes theorem is verified, right? Now we can take one more example as an application of this Stokes theorem. So let us solve this problem here. See here. Now evaluate f dot dr over the curve S, where f is given and c is the curve of intersection of the plane. C is curve of intersection of the plane y plus z equals to 2, and the cylinder x squared plus y squared equals to 1. Right, so here we can see that this is what we get at the intersection of these two uh, plane and the cylinder, right? Two surfaces. Now, to solve this integral, we need the parameterization of this curve C, and we can parameterize and solve. But instead of doing that, we will solve it using the surface integral by finding the curl dotted with n ds over the surface. So the curl is simply this determinant, and we get it 1 plus 2y k, right? So, and for finding the n again, what we can do is we can uh, consider this equation. This equation here is plain as z plus y minus 2 equals 0. Say that this plane is a level set of this function, and if we differentiate with respect to x, we got 0, with respect to y we got 1, with respect to z we got 1. So this is the gradient of this function. Gradient, say let f such that this functions the gradient of the function, and this is nothing but it's the normal vector to the surface, right? So the normal vector we have this one, and 1 plus 2y k dotted with 0 1 1 we will only have this kth component, so we will get 1 plus 2y. Now we need to integrate this 1 plus 2y, but before doing that we need to find the limits over s 1 plus 2y ds. So we need to find the limits here. Okay, so we will use the same parameterization as we did in the previous problem. So the part here, there is a boundary curve is circular. So the circle we have here has the radius, since it's the cylinder, x squared plus y squared equals to 1. So the radius will be from 0 to 1. And similarly, we can take the level curves. We can find the level curves. These will be circles of this kind parallel to this. circle here, so the radius is from 0 to 1, and since it's a circle, theta is going from 0 to 2 pi, and for y we have y equals r sine theta, so it will be 1 plus 2 r sine theta r dr d theta, and this will be r plus 2 r squared sine theta dr d theta, 0 to 1 and 0 to 2 pi. And now